Hello everyone. Welcome to this live problem solving session for the course Introduction to Galois Theory, which is instructed by Professor Krishna Hanumanthu. This is the final live problem solving session of this course. In this week, we have done several problems, but still, uh, because this is a problem solving session, I will do some more problems. Before that, let's quickly recall some important results which have been done in this week. So, basically, we have covered almost all the topics which we wanted to do in this course, uh, except one thing, that insolvability of quintics, that we have done in the first lecture of this week. So, insolvability of quintics, and we have proved that there are quintics that are not solvable by radicals, but that we have done theoretically. But uh, to prove, to give concrete examples, we have proved that the existence of polynomials whose Galois group is SP. So polynomials whose Galois group is SP, where P is a prime number. So basically what we have done, we have taken a polynomial fx belongs to qx, which has exactly two non-real roots, with exactly two non-real roots. Then its Galois group over Q has to be SP. So that we have done, and also we have done some concrete examples to show that their Galois group is SP for small prime numbers. So we have done some examples also in this case, and we have done some concrete examples so to show how to find the Galois group of polynomials. So some examples to find the Galois group of polynomials. So in particular, for degree 4 polynomial, so for quartics, we know what are the possibilities for the Galois group, and we have given example for each type uh, to show that each possibility can occur. And also we mentioned one test for irreducibility which we have used. This is known as rational group test. So this sometimes helps to decide whether a polynomial with integer coefficients, uh, uh, so which rational numbers can be root of that polynomial with integer coefficients. So this is something like if you have a polynomial n x power n plus n minus x power n minus 1 plus so on, a1x plus a0 belongs to zx. Then you want to check if rational number p by q is a root of this polynomial fx or not. Then how do we check that? If it is a root, then q has to divide an and p has to divide a0. And after this, we have done some more problems. And then we have talked about the famous inverse Galois problem. So this is basically given a group G. Uh, is it possible to find an extension K of Q such that its Galois group is G? So that is known as the inverse Galois problem. And for some particular groups, this already known, but it is open in general. Then slowly we moved on to the topic of primitive element theorem, and in that regard we have proved that for each positive integer n, there exists a field extension k over f with degree n, which has no proper intermediate fields. So which has no proper intermediate fields. And then we have proved one thing that we have used to prove the insolubility of quintics, like the non-simplicity of A. So we have basically give the sketch of the group, but it's doable. And in the end, we have done the primitive element theorem. So which basically states that if k over f is a finite extension, then when this extension is primitive, that means when k is equals to f adjoint some alpha. So this will happen if and only if k over f has only finitely many intermediate fields. So k is a primitive extension of f if and only if k over f has only finitely many intermediate fields. And using the Galois theory, we have proved that a finite separable extension is always primitive. So maybe I can write it here. A finite separable extension is primitive because it can be embedded into a Galois extension, and Galois extension, finite Galois extension. So finite Galois extension is primitive because it has only finitely many intermediate fields, because uh, the corresponding Galois group has only finitely many subgroups by the fundamental theorem of Galois theory. So So by using fundamental theorem of Galois theory, we can say a Galois finite Galois extension has only finitely many intermediate fields. Okay, now maybe we can solve some problems. Okay, so let's start with the simple one. So let F be a finite field which contains subfields. So field containing subfields with cardinalities like 2, 4, 8, 16, and dot dot so on to power 10. Then what is the possibility least possible order of F? What is the least possible cardinality of F can be? And also, how many subfields does F contain in the least possible case? So this problem has two parts. So basically, we have to use the structure theorem of finite fields and also the fundamental theorem of Galois theory. So let's see how to okay. Okay, without using fundamental theorem of Galois theory, this can be done just using the structure theorem. So let's see what it says. So F is a field which contains a subfield of order 2, of order 4, so 2, 4, 8, and so on up to 2 power 10. So all these fields are power of 2. So since these subfields has cardinality some 2 power I, so characteristic of F must be 2, right? Because all the subfields has characteristic 2, so the this bigger field has also be of characteristic 2. So this will imply cardinality of F is 2 power n for some positive integer f. Now when this f will contain a subfield of order 2, 4, and so on. Now f contains, okay, contain subfields of order 2, 4 up to 2 power 10, this will imply this order must divides the order of the field F. So, so this is basically 2 power 1, 2 power 2, dot dot 2 power 10. This will imply 1, 2, 3 and so on up to 10 divides this n. So this is by the structure theorem, right? Because f p power n will contain in f p power n if and only if m divides n. So this is from the structure theorem. Now all this 1, 2 up to 10 divides n. This will imply that their LCM also divides n. So LCM of 1, 2 up to 10 divides n. But what is the LCM of 1, 2 up to 10? So this basically you can see that LCM of 5, 7, 8 and 9 will divide n because these two LCMs are same. So we are taking all two powers of 2 and powers of 3 common. So this will imply, and this LCM you can check that it will be 2520. So this, so we want to take the smallest possible n. So n has to be 2520. Since we want to take least possible n. So this will imply cardinality of f is 2 power 2520. So this is the least possible cardinality of f which contains fields of these cardinalities. So this completes the first part. Now what about the second part? So how many subfields does f contain? So how to find the number of subfields of f? So again we have to use the structure theorem. So again if we use this particular fact that f p power m is subset of f p power n if and only if m divides n. So in our case n is 2520. So basically we have to find the number of positive divisors of 2520. So by the structure theorem of finite fields, the number of subfields of F is same as the number of positive divisors of N, which is 2520. So we need to find the number of positive divisors. And how to find this one? So 2520, if you recall what I have written, it is same as LCM of 5, 7, 8, 9. So it is basically 5 times 7 times 8 times 9. So this is 2q times 3 square times 5 times 7. So this is same as 3 plus 1, 2 plus 1, 1 plus 1 and again 1 plus 1, and you can check that it will be just 48. So this is also a number theoretic function. This is called tau. So we have already introduced one number theoretic functions which is known as the Euler functions, which counts the number of positive integers less than n and relatively prime to n. And this number theoretic function counts the positive divisors. So you just so how to find the positive divisors of this number? So a positive divisors will have the form 2 power sum alpha, sorry, alpha 1, 3 power sum alpha 2, 5 power sum alpha 3, 7 power alpha 4, right? Where alpha 1 has to will be from 0 to 3. Okay, maybe I will write here. So 2 power alpha 1, 3 power alpha 2, 5 power alpha 3, 7 power alpha 4. If this is a positive divisor of n, then 0 less equals to alpha 1 less equals to 3, 0 less equals to alpha 2 less equals to 2, 0 less equals to alpha 3 and alpha 4 both will lie between 0 and 1. So this alpha 1 has 4 choices from 0 to 3. So here this is 4. Alpha 2 has 3 choices. So this is 2 plus 1 3. And both alpha 3 alpha 1 has 2 choices. So total we have 48 choices for positive divisor. So this is how we count the number of positive divisor of the positive integer. So this is the number of subfields of F, and this is this least possible cardinality of F. Okay. Okay, so let's move on to the second problem. So let uh, F subset of L be finite fields. Suppose suppose for any intermediate fields, suppose for any intermediate fields, let's say E and K of this extension L over F. So that means I want to say here we have L and here we have E and K, and this is F. So E and K are intermediate fields of this extension. So for any intermediate fields E and K, either E is subset of K or K is subset of E. Then what are the possibilities? Possibilities of the degree of this extension L over F. So given that L and F both are finite fields, okay, and L contains F, and it has a special property, like if you take any intermediate fields E and K, then either E is contained in K or K is contained in E. Then what are the possibilities of this degree L over F? So we need to find the possibilities of this degree. So L over L and F both are finite fields, right? So since F subset of L are finite fields, so L over F is a finite Galois extension. And not only that, we also know that what is the Galois group, right? It's a finite Galois extension with cyclic Galois group. So that we have already done because the Galois group will be generated by the Frobenius homomorphism. So that means L over F is a cyclic extension. Is a finite cyclic extension. So suppose the degree of this extension is n. So we have to find the possibility of this n, right? What can be this n? So one trivial observation is if this n is 1, then it has no other intermediate field. Then this condition holds trivially because we have no intermediate field. So if n is 1, the hypothesis holds trivially. Because L is equals to F. So it has no other intermediate fields. So this is one possibility. N is equals to 1. Now suppose, so assume N is not 1. Then what can be N? So here we have to use the fundamental theorem of Galois theory. So now by using the fundamental theorem of Galois theory, we can say that for every positive divisor d of n, L over F has an intermediate field intermediate field of intermediate field, let's say k, such that L over k has degree d, because the intermediate fields are in 1-1 correspondence with the Galois group, and Galois group is cyclic. So for every positive divisor d which divides n, we have a subgroup of order d, and that we can from that we can take intermediate field whose cardinality is whose degree is d. So let's use this fact. So if p and q are two distinct prime numbers such that both p and q divides n, so then there exist intermediate fields, say, so what I can use if so say E and K. So E and K such that cardinality of E over F is P, and cardinality of K over F is Q. But in this case, neither E is subset of K nor K is subset of E, because if E is subset of K, then this degree has to be divided this degree, but this is P and this is Q, but P cannot divide Q because they are distinct prime numbers. So I will write down here, because P does not divide Q, and this is because Q does not divide P. So this contradicts the given hypothesis. Which contradicts the given hypothesis. So there is something wrong, right? So we have assumed something wrong. So what we have assumed? This part. So we have assumed that there are two distinct primes which divides n. So this implies there cannot be more than one prime divisor of n, right? So this implies n has to be some p power m, where p is a prime and m is positive integer. So it has only one prime factor. So in fact, the Galois group is a cyclic P group. So this is the possibility. N is either a power of prime or n is 1. So there are only two possibilities. Though that means n is 1 or some prime power. So there are only two possibilities. So basically, in case of finite fields, we can deduce so many things. So I am trying to do some problems in this finite field case, because not much have been done in the finite field case. Not much problems have been done in the course related to finite fields. So okay, now let's do the third one. So again, we will assume the same hypothesis, same condition. So let F subset of L be finite fields, and cardinality of F is some p power m, right? Because finite field has to be of order some prime power. So we are specifying the cardinality of the base field. So now let alpha be an element which is in L but not in F, and Fx belongs to this polynomial ring, be the irreducible polynomial of alpha over F. Now suppose degree of F is k. Okay, not k. K is a bad choice. So let's say it is n. Then show that fx is basically looks like x minus alpha, x minus alpha power p power m, and so on, x minus alpha power p power uh, m times k minus 1. So so we need to prove that the irreducible polynomial of alpha has this particular form. Okay, so let me explain this problem. So let me draw this picture. So here it is L, here it is F, and cardinality of F is p power m. So cardinality of L is also some power of p, but we are not interested in that. And cardinality of L is also finite. But we are taking alpha belongs to L, but alpha is not in F, such that degree of alpha over F is n, which is same as degree of the irreducible polynomial of alpha over F. And we need to find the specific form of this irreducible polynomial of alpha. So that is our task. So how to find the irreducible polynomial of an element? So we need to use the structure of Galois group of finite fields, and also uh, the concept of primitive elements. So how to do this? So let's solve this. So let uh, k be F adjoint alpha, right? So then, okay, let k is F adjoint alpha, and H is the Galois group of k over F. Sorry, not H. Let's take G. Galois group of k over F. So now using the Galois group, there is a way to find the irreducible polynomial of an element. So how to do this? Right. So then, so this is a Galois extension. So let me mention that. Then k over F is a Galois extension, because these are all finite extension of finite field. So the irreducible polynomial of alpha over F is basically has this form, x minus okay, so it is product of all the x minus all the conjugates of alpha, x minus sigma alpha, such that sigma belongs to the Galois group, because these are all conjugates of alpha. So we can find all the conjugates of alpha using the Galois group, and we are taking all the factors. So that will give you the irreducible polynomial. So this is already done in the proof, where we have characterized Galois extension like a finite extension is Galois if and only if it is a splitting field of a separable polynomial. So you can go back to the proof, and you can see that we have used this fact to find the irreducible polynomial of an element using the Galois group. So basically we need to find these conjugates. And how to find these conjugates? So basically we need to act the elements of the Galois group on alpha. In other words, we need to find the orbit of alpha under the action of the group G. So thus we need to find the orbit of alpha under the action of G. So for that, first we need to find this group G. So first, let's find the group G. So let me draw the picture. So here we have F adjoint alpha, and here we have F, and here we have F power P, where P is the characteristic. And since degree of alpha over F is n, so this has degree n. And cardinality of F is P power m. Cardinality of F is P power m. So this is n and this is m. So this simply n times m. And so what will be the cardinality of this? So cardinality of F alpha is basically P power nm. And we know about this particular Galois group, right? So we know this Galois group of, so this is our field K. This Galois group, this is basically generated by sigma, where sigma from K to K is the Frobenius map. Sigma of A going to A power P is the Frobenius map. So we know it is a cyclic Galois, this Galois group is cyclic, generated by the Frobenius map. So this we have already done, and we have already used so many times. So this Galois group is cyclic, so all its subgroups is also cyclic. We need to find this particular Galois group. So how to find this? This will be a subgroup of this Galois group. So if you recall, uh, so then G, which is Galois group of K over F, will be basically generated by tau, where tau is nothing but sigma restricted to F. Sigma, and order of sigma is Nm. Okay, I think we are doing little bit wrong. Yeah, we are doing little bit wrong. So, yeah, this is not a subgroup. So we are doing it wrong. So from the fundamental theorem we know, now from the fundamental theorem of Galois theory, we know, so this extension will be Galois if and only if this Galois group is normal. So Galois group of K over F is basically uh, Galois group of K over Fp quotient by Galois group of F over Fp. These are isomorphic. Okay, am I doing it right or okay, let me check once. K over F, L over F. Okay, so this should be the other way around. So this should be L. This should be F over Fp, and this should be K over F. So and this map, so let's recall this map. So this is defined from K over Fp to this Galois group, where sigma is just the restriction map, and kernel of this map is our Galois group. Kernel of this map is Galois group of K over F. So this is sigma, all those elements in this element which maps to identity, such that sigma restricted to F is identity, right? That is the thing. So basically we don't need these things. So we want to find this Galois group. We know this Galois group, and this is a subgroup. Sorry, this yes, this is a subgroup. So let me write. We want to find Galois group of K over F, and we know Galois group of K over F is a subgroup of Galois group of K over Fp, which is generated by sigma. So which is a cyclic group, and we want to find this cyclic subgroup. And so how to do this? So okay, we don't need this part, so let me erase. So this will imply uh, the Galois group of K over F is generated by some power of sigma. But what is that? So cardinality of Galois group of K over F is n, So this order of this element has to be n. So let me write this tau as tau. So where order of tau is n, but we know sigma has order nm. So this will imply tau is equals to sigma power m, because order of sigma power m is n. So this will imply tau of a is basically a power e power m for all a belongs to k. So we have found the Galois group. So now let's find the conjugates. So therefore fx is basically product of x minus how to write uh, okay, not f. Okay, so let's say beta of, not beta. Okay, maybe you can write sigma prime of alpha, product of these factors, where sigma belongs to the Galois group of k over f. So this is x minus tau alpha, x minus tau square alpha, and so on, x minus tau power n alpha. So what is this? So x minus sigma power m alpha, x minus sigma power 2m alpha, and so on, x minus sigma power nm alpha. But sigma power nm is just identity map. So this first thing is alpha power p power m, x minus alpha power p power 2m, so on, x minus alpha power p power m times n minus 1, and the last factor is x minus alpha. So this is the thing which we wanted. Okay, so L over F is a finite field. L over F are finite fields. We are taking alpha belongs to L but not in F. So we want to find the irreducible polynomial of alpha. That is the thing. And it has this x minus alpha power p power m, x minus alpha power p power 2m up to so on, x minus alpha power p power m times n minus 1, and x minus alpha. That's all. So just go through the proof. It's not difficult. We have to just find the Galois group of this part to find the conjugates of alpha. And once we know all the conjugates of alpha, we can easily write down the irreducible polynomial. Okay, let's move on. So this is problem number 4. So this is a true false type question. So let fx belongs to fpx be a separable polynomial. Then there exists a positive integer n greater or equals to 1 such that this fx divides the polynomial x power p power n minus x. So this is true or false. So we know Fp is the finite field with p elements, where p is a prime number, and we are taking a polynomial fx from Ftx, and which is separable. Then fx must divide this polynomial x power p power n minus x for some positive integer n. So this is true or false. Okay, so let's try to solve this. So how to do this thing? How to check it is true or false? So we this is already a separable polynomial. So let K be the splitting field of Fx over Fp, right? So then uh, K over F is a finite Galois extension because it is a splitting field of a separable polynomial. And not only that, uh, since F is a finite field, so sorry, Fp, and cardinality of F is p power n, since K is a finite field, because splitting fields, so this K over F is a finite extension, so K has to be a finite field. So since K over F is a splitting field of F, so K over F, sorry, Fp, so K over Fp K over Fp is finite, so that will imply cardinality of K is also finite, because K is a finite dimensional vector space over a finite field. And by structure theorem we know by the structure theorem of finite fields, we know elements of K are basically the roots of the polynomial x power p power n minus x belongs to Fpx, right? Because this is how we have constructed finite fields. This is how we have proved the existence of finite fields. So K and this element contains the roots of f also. Contains the roots of fx. So that will imply fx must divides x power p power n minus x. And because fx is separable, so it has no multiple factor. So all it has only simple roots, and all the roots are roots of this polynomial also. So this is true. So there exists some n such that fx divides this polynomial. So this is just by using the Galois. Uh, so do we need Galois extension? So we don't need Galois extension. We just need that it's a splitting field, and we need. Uh, so we just need it's a finite extension. Let's erase this word. Okay, so we can remove this thing also. So we just need the structure theorem of finite fields. Maybe we need to assume it's a separable irreducible uh, according to our statement, according to our definition. Separable irreducible polynomial. Then it cannot have multiple roots, and all the roots are roots of this polynomial. So fx must divide this polynomial. That's all. Okay, now maybe let's do some problems to see how to find primitive elements. So this is problem number 5. So determine a primitive element uh, of a subfield K of the field E Q adjoint zeta 13, so that this cardinality of K over Q is 3. And what is zeta 13? Uh, zeta 13 is a primitive 13th root of unity in the field of complex number. Okay, so this is the notation which we have used. So this is the cyclotomic extension, 13th cyclotomic extension of Q. Zeta 13 is a primitive 13th root of unity. So we need to find, okay, maybe I can draw. So here we have Q adjoint zeta 13. Here we want to find primitive element for K, and here we have Q. So that this becomes 3. And we know this degree. So this degree is basically P minus 1. 13 is a prime number. So this is 12. So this must be 4. So we know the Galois group of Q adjoint zeta 13 over Q is simply the multiplicative group of Z mod 13Z. And this is a cyclic group, right? That we know. So this is just all the elements which is relatively prime to 13 and less than 13. So 13 is a prime number, so all the elements will be here. So let's say it is G. So G is a cyclic group of order 12, and you can verify that G is generated by 2. So you just check that order of 2 is not 6. So verify this. So this will imply the Galois group of Q adjoint zeta 13 over Q is generated by sigma, where sigma from, okay, this is our E. So maybe we shall use this shorthand notation. So where sigma from E to E is defined by sigma of A is A square. But what we want to do? We want to find a primitive element of this subfield. So now K is basically EH, where H is a subgroup of G of order 4. So by the so this should be E power H, and this should be cardinality of H, and this should be index of H in G. So this is by the fundamental theorem. So so this will imply H is generated by sigma power Q, because order of sigma power Q is 4, since order of sigma is 12. So we have the Galois group of K over Q. So this will imply Galois group of K over Q is H. Is it, or E over K? Okay, sorry. This should be the other way around. E over K. So now a primitive element a primitive element of k over q is basically, so sigma q applied to zeta 13 plus sigma q square, which is 6, applied to zeta 13 plus sigma qq, which is 9, applied to zeta 13. Finally sigma power 12 applied to zeta 13. This is simply, you can check. So sigma of zeta 13 is zeta 13 square by the definition of sigma. So this is zeta 13 power 6, sorry, square. So zeta 13 power 2 power 3, which is 8. This is zeta 13 power 2 power 6. So we will get, oh, am I doing something wrong? Yes, it's correct. Power 12, because its power 13 is 1, plus zeta 13 power 2 power 9, and we have to modulo by 13. So it will be 5, and finally zeta 13. So this will be a primitive element. So this is a process to find the primitive element using the Galois group. So we need to find an element which is not fixed by any element of the Galois group. Okay, maybe now we can do one easier one. Problem number 6. So find the degree of the extension q adjoint zeta 3 comma zeta 7 over q adjoint zeta 3. So this zeta n is actually the primitive nth root of unity in complex numbers, field of complex numbers. So we need to find this degree of extension. So we have already done one problem uh, using that. You can see that. So zeta 3 times zeta 7 is a primitive uh, 3 into 7, which is 21th root of unity, because 3 and 7 are co-prime. So you can verify this, or go back to the uh, previous problem solving session. I have done this thing in the previous classes. So you can go back and take a look. So this will imply q adjoint zeta 3 zeta 7 is basically q adjoint zeta 3 zeta 7, which is same as q adjoint zeta 21. So this, so I am doing this first, so maybe you can verify all these things. So what is the thing? Mm, so here we have zeta 21, and here we have q adjoint zeta 3, and here we have q. So this is 20, zeta of 21 is phi of 21, which is 2 times 6, maybe it is 12, and this is 2. So we need to find this part. So this will imply q adjoint zeta 21, q adjoint zeta 3, this is 6. Yes. So using the multiplicativeness of the degree, we can easily deduce this thing. So I'm leaving this part to verify to you. So you can do this thing. Yeah. So maybe this much problem is enough. So as this is the last problem solving session, we will not have any chance to discuss more problems. But still, if you have any doubt, you can just post in the discussion forums. Okay. So maybe then we can stop now.